And the talk today is by Peter Miller, actually, who's in both programs. So I think we have people from both programs here. And it will be on algebraic solutions of Painlev tree.
Thanks, Edward. Thanks everybody for coming to the talk, and I hope I can explain some interesting features of solutions of the E7 variety of the Painlev equation. What I want to discuss is joint work with Robert Buckingham, who's at the University of Cincinnati, and also at the beginning I'll show you some things that we did with Thomas Botner, who was a postdoc with me at Michigan, but now he's at Bristol, and Yue Sheng, who is a master's student at Michigan, and now I found out he's in Google, right? And I found that out by Google. So, okay. So these are the Painlev equations. They were discovered in an attempt to classify second-order nonlinear, non-autonomous differential equations for a function u of x that have a certain magical property, namely that all of the singularities of the solutions that can be changed by changing initial conditions on the solution or for the equation are just poles, and that's called the Painlev property. And it turned out that that all such equations could be reduced either to known equations or to these six equations that we nowadays call P1 through P6, just like that. And so all of them, except for this Painlev 1 equation that's done in gray here, they've all got one or more constant parameters in the equation. So like an alpha in Painlev 2, for instance. And that's really important for sort of having a wider variety of solutions, because you can vary the parameter as well as the initial conditions for the equation. Okay. So, although it's the case that typical solutions of these equations are highly transcendental functions, it turns out that all of them except that first one, the Painlev 1 equation, all of them except that one admit special solutions when the parameters have special values. And these solutions are kind of simple. They can be expressed in terms of elementary functions, or sometimes you can also express them in terms of classical linear special functions like Carey functions, Bessel functions, and so on. So it's not the typical thing, but if your equation has parameters, then you can find special values of the parameters where something like this is true. And those parameter values where the magic happens, they are related to each other by some finitely generated group action. So you might think of like a lattice of parameter values, integer values, something like that. And then that group that is moving the parameters around in this special family, that group also acts on the solutions, on these special solutions of the equation via a Becklin transformation. So these are some kind of transformations of the function u and u prime, and they have the effect that they preserve the functional character of the solution. So if we start out with a rational function and we apply a Becklin transformation, what we get out again is a rational function. Also algebraic functions, etc. Okay. So going through the history, one finds that Ricard Fuchs and Garnier, they made the observation very early on after these equations were written down that every one of those Painlev equations, all six of them, they define isomonodromic deformations for some linear second order differential equation. This was known a long time ago, but it was only rediscovered more recently, and now we have a whole theory of how to take advantage of this. And the modern version of the theory works more with first order systems instead of second order differential equations. So if we do that, then we get some kind of a 2x2 matrix psi, which is the stand-in for the solution of the second order linear problem. And every Painlev equation is the compatibility condition for a certain lax pair, it's called, of linear equations for this matrix psi. Okay. Then we may think about, for isomonodromy problems, you might think about knowing the monodromy group and trying to reconstruct the coefficients or build the differential equation from knowledge of the monodromy. And that inverse problem is frequently formulated as a Riemann-Hilbert problem in the complex plane. Okay. Now we talked about this symmetry group of the parameters and the Becklin transformations of the solutions of the Painlev equations. Well, that same group also acts on this psi that solves the linear equations. And it acts as a linear gauge transformation, and that's called the Schlesinger transformation in this business. And the Schlesinger transformations have the feature that they're leaving the monodromy data invariant for the Lax pair. But what they do is they change some formal exponents at singular points that really encode the exponents are what encode these parameter values that are special for the equation. So you apply the Schlesinger transformation, you change some exponent by an integer or something like that, and you're moving to the next point in the parameter space, picking up also the next special solution of the Painlev equation. Okay. So what it means for us is that, that if you can find sort of a Riemann-Hilbert representation of just one solution in this family that we usually call the seed solution, then you may apply these transformations and consequently write down very quickly the Riemann-Hilbert representation of the entire family of special solutions. So generally speaking, it would be a hard problem to write monodromy data down because it requires solving the linear differential equation and extracting information about its solutions. It's a non-constant coefficient problem, generally speaking. So generally we can't get the monodromy data. But on the other hand, if you think about the seed solution, this very special solution that can start the whole game going, that seed solution is usually very simple. And if you put that into the coefficients of the Lax pair, what you usually get is some differential equation in this variable x, the independent variable x, that you can actually solve, a linear differential equation whose solution can be given in terms of classical special functions. So what it means is that if you start with the seed and you play your cards right, then you can compute the monodromy data for the seed just using connection formulas for classical special functions, area functions, Bessel functions, and so on. So at that point, what it means is you can use the Riemann-Hilbert representation of the whole family because you have that available to you now. And you can deduce useful information about the family of special solutions, especially in the interesting case where you drive the parameters very far away from the seed values. So you think of large values of the parameters, extreme values, and then you can use asymptotic methods for Riemann-Hilbert problems like the steepest descent method. Okay. So what I've just described to you is kind of an algorithm for understanding certain special solutions of Painlev equations. And we may call this the isomonodromy method. It has been applied successfully to rational families of rational solutions of several of the Painlev equations. So here's some examples. So that if we take the second Painlev equation, that had a single parameter called alpha in it that I highlighted earlier on. And if that alpha is an integer, then there is a unique rational solution of the equation. That can be shown fairly easily. And so the seed solution is a simple thing like a constant function. And so if we evaluate the Lax pair, which is due to Jimbo and Miwa on that seed solution, then we may solve the Lax pair explicitly in terms of area functions. So that's like these are the classical linear special functions that show up when we solve the Lax pair on the seed in the case of the Painlev 2 equation. Going up by even numbers, we can jump to 4, the Painlev 4 equation. So this one has two distinct families of rational solutions. They're built out of special polynomials called generalized Hermite and generalized Okamoto polynomials. And so in this case, there are each one of these two types of polynomials, two families of special polynomials, is indexed by two integers. So we have two integer parameters in our family. And in the case when we start with generalized Hermite solutions and we pick the simplest case as our seed, the Lax pair can be solved just in terms of elementary functions. You don't need anything more than exponentials for that. And in the case of the generalized Okamoto rational solutions, in this case, you have to use area functions, just like we did in the case of Painlev 2. Okay, so that's about rational solutions of P4 and P2. And now I would like to interpolate and tell you something about the rational solutions for the third Painlev equation. Okay. So the first thing we have to worry about is that the third Painlev equation has 4 parameters in it: alpha, beta, gamma, delta, and those 4 parameters can take bad values. Okay, so there's a generic version of the Painlev A3 equation, which people call the D6 type equation. And that one, what makes it generic is the fact that the product of gamma and delta is non-zero. Okay. So in that case, by some scaling, some simple scaling of x and u, you could choose gamma to be equal to 4 and delta to be -4. People usually do that. And then the parameters that are left over are alpha and beta. And it's convenient for the subsequent discussion here to write those as 4n plus m for alpha and 4n minus m for beta. So now if you do that, then the third Painlev equation takes this form here. So here's the simple coefficients that we scale to 4 and -4. There's alpha, and over here's beta, just like that. So the reason for using the m and the n are that this equation is known to have a rational solution if and only if either of these two numbers n or m is an integer. So if both of them are integers, then you get 4 rational solutions. But if only one of them is an integer, then you get 2 as it happens. So it turns out that even though that seems to be a case of distinction, on the other hand, you can get all of them, whether it's 2 or 4, you can get them by some simple like rotation symmetry in the complex plane. So it's good enough to assume that, say, n is an integer. And in that case, there's a unique rational solution, which we call un of x with the second parameter m floating around here, that has the property that at infinity it's equal to 1. And if you know this one, then whether m is an integer or not, you can get all the other rational solutions from this use of n function. Okay. So when n is equal to 0, in this case, the function un turns into just a constant function 1, which could hardly be simpler. And that's the seed solution for this family of rational solutions. Okay. So we have 1. That's very good. And now I need to show you the Lax pair for the Painlev A3 equation. So this was in the paper of Jimbo and Niwa. They have this 3-part paper from 1981 about isomonodromic deformations of differential equations. And it's in part 2 where there's an appendix that they list off all of the Lax pairs for the Painlev equations. So that's a useful reference for you if you want to look those up. So they give the Lax pair for the D6 equation. And the way they write it is to not write something with u, which is our solution of Painlev A3, but to write a pair of linear equations that have 4 functions called a v, y, s, and t. And there's also a parameter theta infinity, which in terms of our m and n is just this combination m minus n plus 1. So you see that there is a differential equation for this matrix, or if you like, column vector psi over here with respect to lambda. Lambda is like the spectral parameter. We think of that. It's this auxiliary parameter for the Lax pair, or it's the parameter in which we compute these isomonodromic deformations. So anyway, so here's a differential equation for deep psi d lambda. And it's got a matrix coefficient here that involves this parameter theta infinity, and then the potentials y and v are off diagonal with its coefficient of 1 over lambda. And then the most singular part at lambda equals 0 is this kind of messy looking matrix that has x is our independent variable, and s and t are potentials in the problem. So this looks complicated, but what it really is just a matrix whose eigenvalues it's the most general thing really, because eigenvalues are plus or minus ix over 2, which is the same really as this coefficient over here. So those two have the same eigenvalues, and it's just that somehow in the gauge that Jimbo and Niwa wrote it down, they decided to make the leading terms at infinity here in lambda, the largest terms when lambda goes to infinity, diagonal. That's what they did. And then you pay the price over here. So that's the lambda equation. And then you think of, okay, what are the flows with respect to x here? Okay, that I'm going to flow this matrix psi with respect to x in such a way that I preserve the monodromy of the monodromy group of this equation. And this is the isomonodromic deformation equation down here. And so again, we see the same complicated looking matrix coefficient and a diagonal term at infinity like that. Okay. So if you like, you can do it the other way around. You can diagonalize this one, but then you pay the price over here. So what you do is you take these two equations and these are simultaneously holding true for some function psi of both variables x and lambda, and that requires some kind of conditions on these coefficients for that to be admissible. So you can compute the compatibility condition of these two equations, or write down what's called the zero curvature equation. Those are the same thing. And what that is it's a first order system on the variables of v, y, s, and t as functions of x, is what it is. So you get such a thing out, and that system you can check has a first integral or constant of the motion. There's a combination of these four functions that's independent of x, and that one is called theta naught in the theory. So that's actually n plus m for us. And this system of four ODEs, once you reduce out by the constant theta naught like that, then you can write down or deduce from it the second order equation, that's the Painlev equation on the function u, which is just minus y over s. That's sort of how you get ultimately the solution of Painlev out of this system. Okay, so that's the kind of the general thing. So what you would do in general, if you're trying to solve a problem with the Painlev equation, is you would say, okay, given some information about u, maybe I know the value of u at some point and its derivative. Then I try to work out what the values of v, y, s, and t are at that point, and I put all that information into this equation. And now I have some differential equation that's non-constant coefficient because of lambda and lambda squared, but these are constants here, these matrices. And I try to solve that and deduce the monodromy group of this differential equation. And then from that, I'm able to tell that the monodromy is unchanged under flowing with this equation, and the compatibility condition between these two tells me that actually when the potentials change, these coefficients are varying in time. Sorry, with respect to x here, and that's happening. I'm getting a solution of the third Painlev equation, that's this function u of x. That's kind of how the procedure works. But it's a lot easier if you know something about the solution, like we know that the seed solution for this function is the constant function 1. We can take advantage of that. Okay, so yeah, so when n is equal to 0, that's the seed value of the parameter. Then all of these auxiliary potentials in the problem, they are all very easily written down explicitly in terms of this constant function 1 for u naught. And so we had a paper with Thomas Botner and Yu Sheng, where we solved the x equation, the second one in that Lax pair, using the fact that the coefficient's dependence on x was so simple. And what comes out is that actually that equation is really the confluent hypergeometric equation in disguise. And so you can write down a solution in terms of Whittaker functions. Once you have the solutions in terms of Whittaker functions, then you should do something like, okay, lambda equals 0, lambda equals infinity are special points for the problem. So you should do some kind of normalization, find a good way to represent solutions near those points at 0 and infinity in different Stokes sectors. And consequently, you're computing some canonical solutions in terms of Whittaker functions. And so you really solve what's called the direct monodromy problem. As it happens, 2 Stokes sectors at each of these 2 points on the Riemann field. Okay, so now you know kind of what the solution looks like for the seed, and then you may use connection formulas for the confluent hypergeometric equation to see how the solutions in the different Stokes sectors are linked to each other, and consequently you get some kind of multiplier, matrix multipliers that connect those solutions together. So that's the data for a Riemann-Hilbert representation of this seed solution. Okay, I get it. This is just the function 1, but nonetheless, it's a Riemann-Hilbert representation of 1 somehow, and its related potentials when n is equal to 0 through these matrices of connection. Okay, and then we talked at the beginning about these Schlesinger transformations that act on the psi. And so what those do is they are going to leave the jump matrices, these connection matrices, basically alone. They're not changed at all, but they will increment or decrement some so-called formal monodromy exponents, powers of lambda at 0 and infinity in the expansions of the solutions. And what this amounts to doing in terms of our parameters from the problem is shifting this index n by integer up and down. So what we're really saying is that, you don't mess with the jump matrices, you just change these exponents by integers explicitly in the Riemann-Hilbert problem. And then you are looking at the Riemann-Hilbert representation of this function un of xm for any integer n. So even though you started with somehow the trivial solution, now you have the data for any solution in the same family. Okay. So, so when you have that Riemann-Hilbert problem in your hands, I mentioned then at the end that that introduction slide that, what you should do is think about the parameters being large. You could really exploit this representation to figure out what these solutions, in this case, these rational solutions look like when n is very large. So we did that in a subsequent paper with Thomas Bodner. So we applied this, what's called the Date-Joe steepest descent method to that Riemann-Hilbert problem, and I won't tell you the details of what we did, but I will tell you the answers because it's kind of interesting. So first of all, there's kind of a general case. The general case is that n is an integer that's big, and the m is not a half an integer. So that means I want to take z plus a half. I want to avoid those points in the complex point. Okay. So if that's the case for m, and you make n very large, so n is a fixed number like that, and n is a large integer, then it turns out that what comes out is that there's a well-defined and independent of the second parameter m domain in the complex plane that we call E. It's sort of shaped like an I, so we use E to denote it. Here's the shape of it. And it has this domain E is such that when X is in a scaled by n version of E, so we expand out the size n, this I, okay, when X is there, this function un of xm is very accurately approximated by a specific elliptic function of X that we calculate. And that elliptic function has a phase shift and an elliptic parameter that actually change as you move around inside of this I. So from point to point in the I, like over here, you can see that the grid of these poles and zeros is kind of lining up in this way, but down here it's different, right? And that's because there's been a modulation of that elliptic parameter as we move through the I like that. But locally, near any fixed point of the I, you let the n go to infinity, and you're going to see an elliptic function with a specific modulus and phase shift. So another interesting feature is that modulation, as you vary through the I, is decidedly non-analytic, which is interesting because, of course, the function we're approximating is a rational function. But somehow, when you do the asymptotics, what comes out are some quantities that solve d-bar equations. And so in the I, there's some kind of non-analytic dependence on the slow version of this variable x, the scaled version of x. Okay, and outside of the I-shaped domain, when x is outside of the scaled I, this un is approximated instead by an analytic function of this fraction x over n, sort of slow variable. So in particular, it's analytic, it's also non-zero, so there are no poles or zeros of the rational solution asymptotically outside of this scaled I, like that. So this picture, just to show you what's going on here, so the black curves are the boundaries of the I, and then I think I picked some large value of n, and what you're looking at here, the red dots are the poles, and it turns out there are two factors in the denominator. So I put the poles of one factor as being solid dots, and the other ones are unfilled, okay? And then similarly for the zeros, there are two factors in the numerator, and so blue filled and unfilled dots are those things. And so that's like the picture of the poles and the zeros. It looks like some accumulation is going on here. There are a lot of poles and zeros near the origin, but of course it's a rational function, so finitely many, right? But it looks like a lot of them are there. The asymptotic density of the poles and zeros, in fact, is infinite at this point, but that's something that comes out by taking the limit into infinity. Another feature I'll mention is that since we have these elliptic function approximations, we can also locate the poles and zeros fairly accurately. So here are some kind of, you see there's two families of curves that are kind of orthogonal roughly in the picture. And what's happening is that the intersection points of the two families of curves are good approximations of these unfilled blue zeros. You can kind of see them hitting the intersection points like that. And then there's other curves for the other blue zeros and the other zeros and the two types of poles. So I made one picture of them. Okay. Yeah, so that's what happens. Thomas likes to call this picture the Eye of Sauron from Lord of the Rings. Okay, so these two types of approximations, the one inside of the eye shape, which is like an elliptic function that's moving, modulating around, or the exterior thing, which is some analytic, non-vanishing analytic function, what these really could be thought of as is that they're non-equilibrium and equilibrium solutions, respectively, of a certain autonomous approximating equation. So the Painlev 3 equation is a nonlinear, non-autonomous second order ODE, but in some way, which I'll try to explain a little bit later, you can approximate it by something that's autonomous locally, like you pick a point here and you approximate it as an autonomous equation, and you discover, oh, it might be, you know, the differential equation for elliptic functions. Okay, but anyway, I'll explain some more about that later. So that's the general case, that m is not allowed to be a shift by a half of an integer. Okay, but if m is a half added to an integer and n is large, okay, so then what happens is that actually somehow the equilibrium approximation that was good outside of this eye-shaped region, it actually extends inside the eye from one side or the other only. Okay, so there's what's left over is the other side, which is like we call it an eyebrow. Okay, so like here is the vertical eyebrow on the right side, for instance. And what happens is that that's the place where the poles and the zeros tend to line up. So it kind of looks like rings of Saturn or something like that. You see these kind of curves that we can plot that localize these points. And the number of curves that you get roughly parallel to the eyebrow, depends on the size of this half integer m. Okay, so the bigger m is, the more of these curves there are, but they're all sort of getting attracted to that eyebrow in the limit n goes to infinity. Everything is localized there. So that's kind of interesting. And the situation that m is a half shift of an integer, the reason that that's different, okay, in the problem is that all of these these jump matrices that relate the solutions of the psi in different Stokes sectors, they're all either upper triangular or lower triangular, depending on whether m is positive or negative as a half integer. And so what it really means is that there's some simplification that takes place. The algebra of multiplication by triangular matrices is simpler than full matrices, and things sort of simplify in some way. And the simplification is related to like the representation of orthogonal polynomials by the method of Kokaskis and Kitaev, if you know something about that. So really, in some way, orthogonal polynomials are actually in the background in these special cases. Okay, they're Bessel polynomials actually. All right. All right, so now I want to go back to this D7 equation that was in the title of the talk. So that's another variety of the Painlev 3 equation. And what distinguishes it is that the parameter gamma is 0. However, now we demand that alpha times delta is non-zero. So here's the equation written out now. So alpha, beta, there's no gamma, and then here's the delta over U term like that, and alpha times delta can't be 0. So what's different here is that this equation no longer admits rational solutions at all. There's no rational function that solves this differential equation. However, if alpha is positive, beta is 2 times an integer, and delta is -1. If that's true, then there's a unique algebraic solution of the second order equation. It turns out that it's a rational function of x to the 1/3, and because this beta is 2 times an arbitrary integer n, we should put an index n on that function. So we can simplify the problem a bit, because if you scale x and u by the same constant c, that has no effect on beta or delta, but it does affect the alpha. So without any loss of generality, we could decide that alpha is equal to 8. That turned out to be convenient. And then in that case, the seed solution is just exactly 1/2 times x to the 1/3. So that's what happens when n is 0 and beta is 0. You get this function 1/2 x to the 1/3. But more generally, if you think about arbitrary n that's not 0, then the solution looks still like 1/2 x to the third as x tends to infinity, with some correction term like that. So that's the basic behavior at infinity is still the same as it is exactly true for all x when n is equal to 0. Yeah.
Why do you call these algebraic solutions here for n and 0 if they're rational functions?
They're rational functions, but of x to the 1/3. So they're not rational functions of x. I don't know. That's why people call them algebraic. Okay. So, okay, yeah, so then, but they're close to rational, right? So this function is a rational function of the combination x to the third, which we can call capital Z. Sorry, Z, and it can be represented, therefore, as a rational function as a fraction of polynomials. It's not quite just the numerator and the denominator. You have to do some factoring, but the relevant family of polynomials are known as the Oyama polynomials. There's a sequence of them, P0, P1, and so on. And they're in fact defined by this recurrence relation here. So you start out with initial conditions. P0 is the constant function 1, P1 is 3z squared. And then this is the recurrence relation for the PNs. So if you see, if you want Pn plus 1, what you have to do is divide through by 2√3z Pn minus 1 on the right-hand side. And then you can calculate it. Now, if I say that to you, you will say to me, well, how do I know that Pn plus 1 is then actually a polynomial? And I will tell you that Oyama knows the answer. I'm not sure, but it's really true. Okay, you can check that. But anyway, it's not an obvious recurrence, I have to say. So anyway, so what you're supposed to do to build the solution is you take so un of x is just this Pn plus 1 times Pn minus 1 divided by 2√3 Pn squared, all evaluated when z is x to the 1/3, just like that. And that's a sort of closed formula in terms of this recurrence for polynomials of the algebraic solution of the D7 equation, just like that. So one thing is you see down here that, well, at least if the Pn has, they all have simple roots, which I think is true, then you have Pn squared in the denominator, and that means that you're going to have double poles of this function. So all the poles should be double poles. Okay, but anyway, one thing you can do is you can go and code this up very easily, this recurrence, and you can calculate these. And then you can see the zeros, right? So then those are going to locate the zeros from the numerator, also the poles from the denominator. So here's just some plots like that. So here are the roots of P5 in the z-plane, and P10 and P20 all plotted in the z-plane. So you see that somehow it looks like you're getting this kind of bow tie shape like that, something like that. Maybe there's a neck in between, kind of hard to say. The shape is clearly expanding as n is increasing, and you're seeing more of a pattern in these points, right? So, I mean, anyway, it's just a heuristic observation, making some plots, but it looks like there's something to be explained about this pattern. What are these curves, if you can find them, and so on? What's happening inside here? And so this is a phenomenon that should be explained, but it's a phenomenon about the limit n going to infinity, is the point, right? That's when this picture is becoming something that we can describe by some rules, or say that there's a well-defined boundary or something like that. Not over here, right? Okay. The last time I gave this talk, I wore a bow tie. I never really do that, I don't dress up very much, but I wore a bow tie. People remember that. Okay, I had to buy one on Amazon. All right. Right, so now I want to tell you a little bit about this kind of autonomous approximating equation business, but I want to tell you about it in the D7 setting. So it's a scaling formalism, really. So if you think of n being a large parameter so here's the D7 equation written with our alpha equals 8 and our delta is -1, and here's beta 2n, right? So let's think of n being large and just do like, balance arguments or something like that. So you can pretty quickly see that if you try to scale u by some power of n, and you can try to scale, x by another power of n, and maybe add on a correction, something like that. So you pretty quickly arrive at n to the 1/2 for the right scale of the dependent variable, and for x, n to the 2/3 times some y plus 1/n times z, something like that. So you think of this as like a, y is a constant here. I'm going to basically scale x like n to the 3/2, but then I want to add some correction term, and I want to think of this as the new independent variable. So this is a map from x to z for some fixed y that I pick. I try to think of this as a map from x to z. So then if you plug this in and you use the chain rule to compute the derivatives, then this equation becomes an equation on capital U of z, which is exactly written here. And there's some terms that I'm not writing in all details, but what you have to know about these terms is that there's a 1/n in front of everything here, okay? And n is gone from this part of the equation. There's a 1/n over here. The y, I want to remind you, is just a parameter. It's just a constant parameter. So now you think, okay, if I were to drop this kind of error term, it looks like an error term anyway, it's formally small, then I will obtain what's called the approximating differential equation for the solution of D7, which is just this stuff I'm circling. And because it's an approximation, we use a different letter for it in our paper, which is this kind of U brev thing. Okay, so U brev of Z is the solution of this equation without this correction term. So this is a differential equation of second order, nonlinear, but it's autonomous because the y is just a constant parameter. Okay, for every y, it's a different autonomous equation. That's the approximating equation. Okay, so then I mentioned that there should be kind of two types of solutions of this equation. And so we can play the game here for this one as well. There's the approximating equation again. So one kind of solution is a solution that doesn't actually depend on z at all. So all the derivatives should be 0. This is 0, this term is 0, and then I have to set this to 0. And that's just rearranged as a cubic polynomial. So I want to solve this equation. Remember, y is a constant here. So I try to solve this thing for u brev as a constant function. Well, when y, this parameter tends to infinity, then there's obviously a solution I can get from just this term balancing with this term. So u brev should be like 1/2 y to the 3rd. Of course, the cube root is ambiguous, so I could rotate by e to the 2 pi I over 3 or twice that or whatever. So rotations by 2 pi over 3. And then if I take this kind of, this formula here, and I just go back to the original u and x variables, then that looks like u is like 1/2 x to the 3rd as x goes to infinity, and we can kind of tick a box in our mind that reminds us of what actually is happening to this function un of x when x is large for every single fixed n. So, okay, so those are the equilibrium solutions. They're really just constants. They depend on y through solving this cubic. And then there are non-equilibrium solutions. So for those, I'm going to multiply by an integrating factor that's not 0 because it's not a constant solution. And then when I integrate the resulting equation, I pick up an integration constant e, and I can write the thing in first order form like this. So u brev prime squared is equal to cubic polynomial in u brev, like that, with some coefficients that are constants. And this is really just the Weierstra equation in disguise. If I just do a little linear transformation of the Weierstra function to get u brev, then I have the same equation here is matched by the Weierstra equation, choosing the invariants G2 and G3 to be these constants over here. So some way you're either going to get something, if you believe this, you're either going to get something that looks like a Weierstrass function, or you're going to get a constant that depends on y by this cubic here. So maybe if you think about that and we think about the bow tie pictures, then we start getting the idea that maybe this function un of x, it might be modeled by an equilibrium solution for x being large, where the equilibrium is matching the known asymptotic for large x. And it might be approximated by some kind of modulated Weierstra function for smaller x. So by modulated, again, what I'm thinking now is that those invariants are somehow things that depend on the slow variable y. And so as you move around in the complex plane a little bit, you should have a slightly varying parallelogram for your elliptic function. But anyway, even if we want to believe that, the trouble is that these formal scaling arguments are totally not rigorous. We just omitted a term from our differential equation. So some proofs are definitely required. And it's also not at all clear where or why one kind of approximation should somehow give way to the other in the complex X plane, right? Maybe there's the boundary of the bow tie, but where's that coming out? Nor is it clear at all how this integration constant E for our elliptic approximation would get determined. It somehow is just a constant. So anyway, so to deal with both of these kind of issues, what we can do is we could say, well, let's go ahead and apply the steps that I outlined earlier in the talk of this isomonodromy method to actually cook up a Riemann-Hilbert problem whose solution encodes these un of x functions, okay? And then we could apply this Dave-Joe steepest descent technique to the resulting problem to really rigorously figure out what's happening when n goes off to infinity. That's the strategy to maybe address these 2 points over here. Okay. All right. So the game begins with thinking about the Lax pair for the equation at hand. And we showed you what that was for the D6 equation, the generic Painlev A3 equation. That was the one that Jimbo and Miwa gave in their paper. And that assumes in their paper, the way they write it with gamma and minus delta both equal to 4. But we talked about the fact that you can scale the equation to get any values that you like of gamma and delta, provided the product of them is not 0. So the thing is that what you can't do is no matter how much you'd like to do it, you cannot just set gamma equals 0 in the Lax pair of Jimbo and Miwa, even after this rescaling, to wind up with a Lax pair for the D7 equation. And there's a really important reason for this, and that is that in order to write the Lax pair for the D7 equation, what you have to do is you have to replace the matrix that used to be standing in this spot as a diagonalizable matrix with eigenvalues plus or minus ix over 2. You have to replace it with a matrix that is nilpotent, not diagonalizable. So this matrix has 0 eigenvalues and cannot be diagonalized. And down here, this is the same matrix again with a slightly modified coefficient in the x equation. So this is the version of the Lax pair for the D7 equation that you can find in this paper of Kitaev and Vartanian from 2004. And their Lax pair involves a constant parameter that they call A. You can see it here and also over here and on the diagonal. And unknown functions P, Q, var phi of x, and u of x, sort of sprinkled in the coefficients there. Okay. So if you compute the compatibility, you assume that those 2 equations are simultaneously solvable, which puts a condition on those coefficient matrices. Then you find out that, okay, so P, the potential P of x is just the derivative of u e to the I phi over x, and something similar for Q of x. Then you get a differential equation of second order for the function u, which sadly also involves the function phi of x like that. And then you have this equation here, which is really something that can be integrated up, put a constant on the right-hand side. And if you do that with a specific choice of integration constant, I think I have I over here for that constant, then you have this identity between u and var phi like that. So at that point, you could notice that over this equation, it's only var phi prime that shows up. So you could solve for that and eliminate it completely, and you're going to get an equation just on u. And that equation is exactly the D7 equation like this. It's written in a slightly different form because of the A. So beta here is 2 times I times A. But that's the equation. By the way, this is the reason we wanted to make the alpha equal to 8 so that we could match with the Kitaev-Vartanian paper, but it's a choice. Okay. So now we want to apply this isomonodromy method. So that means we want to first solve the Lax pair for the seed. The seed corresponds to n equals 0, so beta or 2n is equal to 0, and our u function is 1/2 x to the third. So if we take those nonlinear differential equations on the p and the q and the var phi and so on that we wrote on the last slide, then you can pretty quickly figure out what those functions have to be, knowing this about u. So the var phi turns out to be just 3i x to the 2/3 plus a constant, which we'll just take to be 0 without losing any generality. And so, so that means that these exponential factors that are showing up in the matrices are just simple exponentials, e to the minus plus 3x to the 2/3. And so those are showing up here on the p and the q with some algebraic coefficients like that. So this is just from starting with the seed and writing down these potentials. Okay, so now our Lax pair is going to have exponentials in it, you can see here. And what we'd like to do is not have those. We want to have something that's more algebraic, closer to special function equations. So we're going to get rid of those by a gauge transformation. We're going to write psi as e to the minus 3/2 x to the 2/3. This sigma 3, if you don't know it, is just the matrix, diagonal matrix 1, 0, 0, minus 1 times phi. So then the equivalent system for phi looks like this. There's no exponentials in the coefficients anymore, just some powers of x like this and lambda. So it looks a little bit better. Thank you. Okay, so our strategy going forward is to focus on this equation here. The reason is that here it's a differential equation with respect to x. These coefficients are all relatively simple functions of x. Here's a constant, for example, over here. So maybe there's a chance of solving that in terms of classical linear special functions. Okay. So that's our goal. We're going to solve this x equation explicitly. So, well, it's kind of something you work out gradually, but let's just do it in some steps. So first, it's convenient to scale the spectral parameter. So we're going to scale the lambda variable to write it as capital lambda over x, big X. And little x is the same as big X. And in that case, the change of coordinates that your calculus students should compute for you are here. So these are how the derivatives transform. And so then in the new variables, the capital X, capital lambda variables, then these are the differential equations for this modified gauge transform matrix phi. And now the x equation looks really simple, I think. It's really just got x to the plus or minus 1/3 as coefficients. So what should you do next? It's completely clear, right, that you should call that thing z. So z is the x to the 1/3, and then you're going to have a much simpler equation. So it's also convenient to deal with this coefficient matrix a little bit. So we'll make a constant gauge transformation to capital omega. So this will substitute for z and also capital omega like that as our new variable. And then we end up with this very simple looking off diagonal system like that. This is basically the area equation, but it is in disguise. So all you have to do really is just put some constant. This is a constant matrix as far as z is concerned, a constant left multiplier like this to deal with these lambdas somehow. And then what's left over is really just a fundamental matrix, any fundamental matrix that you like for the area equation. And the independent variable here, this c, is a combination, a mixture of z and lambda by this formula like that. Okay, so at this point we have you pick up a basis for Airy's equation, you have this F matrix, you put in this multiplier, you have a solution now of the x equation. This is the x equation after some transformation. So then we don't want to forget that there's also a lambda in the background. There's another variable. And the general solution of both equations should be written in the form like this. So here's the solution of the x equation. Here is a matrix that does not depend on x, but it may be allowed to depend on the other variable lambda. So that's the general solution now of both equations, really, of the Lax pair C. Okay. All right. So now we want to figure out what this h of lambda is. So we want to take advantage of the fact that this seed solution generates matrices that are compatible. Okay, this is this system of simultaneous linear equations is compatible And if we use that fact, we can very quickly work out what this factor of h of lambda has to be. In fact, it's really a scalar. It's really just lambda to the power 1/6 times any absolute constant matrix that you want. And actually, given that this is multiplied on the right after this F matrix, which was a fundamental matrix for Airy's equation, it really means you could just absorb this into the choice of basis of your Airy functions. So really, this h of lambda is just a scalar lambda to the power 1/6. Okay, so now we go back, take this formula that we got by these transformations, and we just go back to the original variables of the problem, which was little x and little lambda. So now we find that the seed solution 1/2 x to the 1/3, which had these parameter values, the parameter n is equal to 0 for that one. Really, the simultaneous solution can be written like this. So again, we had a diagonal matrix, and there was also a gauge transformation that was constant. So that's all this stuff now. Here's that exponential factor that we took out at the very first step. And then over here, this is the Airy matrix, right? So this is the fundamental matrix for Airy's equation, and the C written in terms of the original variables is just this combination here. So you'll notice that, so the singular point for Airy's equation is that C equals infinity, and that's going to happen when lambda goes to infinity, but also when lambda goes to 0. Right? So both 0 and infinity in the spectral plane of lambda are sort of irregular singular points for this problem. Okay. All right, so now I'm starting to tell you about some things that are in this paper that was recently published with Robert Buckingham. So the general solution formula that I just showed you is branched at both 0 and infinity, and it's also got Stokes phenomenon in both limits, and that's exactly because C goes to infinity, goes to both points in the lambda point. So what you want to do is kind of specify some solutions near 0 and also near infinity in different Stokes sectors as are dictated by the form of the argument of the Airy functions. So it's easiest to do all that in the case when there's this x that's floating around. Let's assume that x is a positive number. That's going to help us to keep things straight in terms of the directions in the complex plane. Then you can draw a diagram that's kind of like this. You see now there's a domain near the origin here, which we call D0, that just avoids this upwards branch cut, really. And then there are two sectors at infinity, E infinity minus and plus, like that. So what we have to do in each one of these sectors is just pick a basis of Airy's equation, okay, in such a way that we have very nice asymptotics near 0 and infinity. So here are the formulas for that. I don't need to really spend too much time on them, but you see, like in the exterior domains, E plus and minus at infinity, we're using the function AI and also one of the rotated versions of the Airy function as our basis. Whereas inside of the interior domain here, we use just the rotated versions in two opposite directions without the Airy. But anyway. You use what you need to use to have some simple asymptotics near those points. So let me show you what these simple asymptotics are that you get. Okay, so we've got three solutions now, three simultaneous solutions of the lax pair for that seed. Two of them are in the exterior domains, that's psi plus and minus at infinity, like that. And there's one of them that's defined inside of this disk here, like that. They're all analytic functions of lambda in the domain of definition in this figure. And the normalization that we achieve by picking these special Airy functions and so on is such that the following is true. So we have this asymptotic behavior as lambda goes to infinity in the two sectors, those sectors. We take this corresponding solution, peel off an exponential factor, and now we just have a series in descending powers of basically lambda. It's convenient to normalize with an I over X here. So it's identity matrix plus a series, an asymptotic expansion in descending integer powers of lambda with coefficients AP of X that you can compute. It also holds in the limit lambda goes to 0 that the 0 solution, after peeling off a different exponential factor and a gauge matrix like this, and a power, 1/4 power of lambda, that we get an asymptotic expansion now in positive powers, positive integer powers of the same combination of variables with coefficients and VP that you can again compute. So that's the simplification that we get. But really, it's this identity that's the important part. That's the normalizations now. Okay, so then we have these three solutions, and they're not independent of each other because Airy's equation only has two linearly independent solutions. So we have in particular this connection formula that the sum of these three Airy functions is 0, and using that, we can relate the solutions in the different sectors explicitly to each other. So you can and I should mention, yeah, you also have to take into account that the mapping from the lambda plane to the argument of the Airy functions have got a branch cut on this positive imaginary axis, so that somehow accounts for something that you have to do when you cross that curve. But anyway, so now you define a single function psi of lambda x exactly to be these exterior solutions in the two exterior Stokes sectors and the interior solution in the interior Stokes sector. And then what you can say is that the boundary value along this curve, you see I put arrows here everywhere, and there's a boundary value from the left of psi, which we call psi plus, and a boundary value from the right that we call psi minus. And those have to be related by some constant matrix. And that constant matrix, you can work it out for each arc of this curve. So here's what they all turn out to be. So just some constants, all coming from this identity. Like that. Okay, so now you have jump data. So, so what we've shown here is that this matrix psi solves some kind of a Riemann-Hilbert problem in the complex lambda plane. And that was something that we worked out for the index n is equal to 0. So by the way, how long should I go? I saw on the side it said 2 hours, but I certainly don't want to do that. What is the
From the most things for roughly for an hour and then questions.
okay, I'm getting closer, so very good. Yeah, so this matrix that we worked out for the seed, it's solving some kind of a Riemann-Hilbert problem. And so the last part of our method is to replace the index n equals 0 by just any integer that we want. And that's done by using these Schlesinger transformations. So I want to explain how it works for this D7 equation. It's a little bit different than it works for some other problems. It actually was interesting for us to work it out. So the relevant gauge transformations that you need are described in this Kitaev-Vartanian paper. So for instance, if you start with n equals 0 and you want to get the solution for n equals 1, what you have to do is replace this psi that we just built, which we'll now call psi 0, with psi 1. And psi 1 is just a matrix multiple of psi 0, left multiplier. And this G is a gauge transformation that you actually build out of this thing. And the way you build it is by this formula here. So I remind you that this A112, this is one of the elements in the coefficient, one of the coefficients of the expansion at infinity of the solution. So this is something that we know if we know psi 0. And these are things that we get from the solution expansion near 0 in the complex plane. So these again are things that we know if we know psi 0. So this is just really, it's just a simple multiplier that we explicitly build, and then we multiply on the left this way. And you can check that the effect of it is actually to preserve the analyticity of the function psi 0 in all three domains. So it's still an analytic function in all three domains, this one, I mean. And also the transformation leaves the jump matrices completely alone, except on these two parts here, which were the parts that were going up. That's where the branch cut is actually for this lambda to the power minus a half. So there, what it does is it changes the sign of the matrices, and that's all it does. Okay. However, even though that's pretty simple, what it does is it modifies the asymptotic behavior at infinity and at 0. So now, if I take this psi 1 and I peel off that exponential factor, now I have the series expansion with some different coefficients, but it has to be multiplied on the right by this half power of lambda over x, okay, just like that. And if you do the same thing at lambda equals 0 with psi 1, I peel off again that exponential factor and this matrix that we had before. Now I have a series again, but multiplied on the right by the same factor showing up, okay? just like that. So in other words, the power, if you like, of I lambda over x to the sigma 3, this has decreased by a half at both infinity and at 0. And these coefficients are different now as a result of the multiplication. So, okay, so going up by 1 in n, we've reduced both of these exponents by a half, if you like. Okay, so let's go ahead and do it again. So we'll now get psi 2 out of psi 1 by a similar transformation. So here you have to, as it happens, replace the ratio of second column entries of the matrix B, B0 here, with the first column entry ratio of B1. As it happens, that's what you need to do to get the right transformation. But you do that, and now this is your gauge matrix. So once again, the analyticity is preserved by the transformation, and it doesn't do anything to the jump matrix V except on those vertical contours where it again flips the sign. So now you're back. Okay, you do it two times, and now the jump is exactly the same. Okay, and then you look at what happens at infinity. So here's psi 2 times exponential factor. The series is coming with some different coefficients. And now we have, okay, we had minus 1/2 sigma 3 before. Now we have minus 2 times a half sigma 3. So we've decremented 2 times like that. The power has decreased again by a half. But at 0, when we take the second solution and we multiply by these factors, now we just have again this series without any coefficient at all. And that means that the power of lambda over x at 0 has now increased by a half, which undid what we did before. So before we decreased, and now we increased, and now we're back to where we started. So this is what's happening, is that every time I apply this transformation to increment the index n, the index or the exponent at infinity is increasing or decreasing, whatever. It's going the same direction over and over again, whereas the one at 0 is just oscillating back and forth. That's what's happening. That's what you discover by doing this calculation. So at the end, you find that this, if you take this psi n matrix now, in general, we have psi n by doing this n times. We peel off an exponential factor and call that W at n. So that solves the following Riemann-Hilbert problem that characterizes the algebraic solutions. So, okay, we're looking for a 2x2 matrix function of lambda that's called Wn, with the properties that it's analytic away from that jump contour in the figure. The jump conditions are, well, I'm going to use a V tilde as the jump condition, as the jump matrix. That's equal to V on all the jump contours except that branch cut where it's minus 1 to the n times V, taking into account that flipping of the sign. Okay, and then I should conjugate by these exponential factors that are appearing here with the correct boundary values, minus and plus on opposite sides of the branch cut where it matters. The matrix W is normalized by this power depending on n here as the identity as lambda goes to infinity. So that index is incrementing with n every time. Whereas at the origin, I should multiply by this matrix factor here. And notice now the exponent has got a minus 1 to the n in it. And that's capturing this flipping back and forth of the exponent. Okay, so in particular, this limit, the limiting value is this E0 n. That's the Riemann-Hilbert problem. And then even though it looks different for even and odd n, you can still build a function un out of this w by a different formula in each case. So it involves always that leading coefficient at 0, the matrix B0n, but it's the product of the second column entries for the even case and the first column entries for the odd case. So then, okay, you can use a dressing argument with that Riemann-Hilbert problem to prove easily that this un function has to be some kind of solution. This thing has to be some kind of solution of the D7 equation with beta equal to 2n. And then you can think about the Beckman transformation that goes with this Schlesinger transformation, the gauge transformation. And that Beckman transformation is going to preserve the functional character. So we started with a rational function of x to the 1/3, and we're going to get such a thing out every time we turn the crank. And so that means that this un of x has to be the unique solution of the D7 equation that's a rational function of x to the 3rd. So that's the Riemann-Hilbert representation. Okay, So for us, it's convenient to do some kind of renormalization to get something that has a branch cut that goes down instead of up, and that's what's illustrated on this slide. So we have a new matrix y tilde, or sorry, y. We have a matrix y whose jumps are now on a slightly different contour. The difference is that there's this extra piece here, which is orange. I'm going to highlight that for the next slide. Okay. It's just the same thing, but easier to work with. Okay, so I want to now tell you a little bit about this n to infinity part. So remember the basic scaling, x is basically n to the 3/2 times some y. So let's also scale the spectral parameter in this way. So lambda is going to be n to the -1/2 over y times some new spectral parameter eta. And so then if you do that, then the fundamental exponent that's showing up in our jump matrices everywhere is really n times something independent of n, and that something is just this quantity here. So then what we're going to do is set z n is equal to some leading factor here that's a constant, except depends on n but not on x or lambda. So we have this times y, and we'll rescale the jump contour as well. And the reason for doing that is just we want that circle to end up being fixed in the eta plane. Okay, so at the end, we're staring at an exponent that looks like n, something really big times something fixed. And so the key in a problem like this to deal with it, it's like doing an integral with a large exponent, is to control that exponent somehow. That's the key. And the way we do it is to introduce a scalar function called g of eta, depending parametrically on y. It's independent of n, it's analytic in the complement of that jump contour. And the thing we want to do is pick it so that if I build this function f of eta as dg d eta minus the derivative of this thing, and I square it, that function should be continuous except that eta equals 0. The function g should actually vanish at the origin, and then there's some constant g0 of y that's like the constant term in a log expansion of the g function at infinity. So I want to pick g so that all that stuff is true. And then if we use a function that has those properties, then we're going to we'll use it like this. We'll just conjugate this z by multiplying on the right, which is going to modify those exponents by adding the g to it, basically. So we do this transformation like that. And then this matrix M now turns out is going to tend to the identity matrix as eta tends to infinity. And we may examine this limit at 0. We can take a limit eta goes to 0 by multiplying on the right by some suitable factor, and that limit will exist. So when we determine this g, we got to think about the fact that this f is analytic except at the origin, and we can use the formula for f to calculate its asymptotic expansion in both limits infinity and 0. And so you look at this and you realize this f has got to be actually a rational function, right? So it's got to be exactly a polynomial, a cubic polynomial in this first argument mu, which is really minus I eta divided by minus I eta cubed. So the mu has to look like this. The only thing I can't tell from these expansions here is what this constant c is. Everything else is determined. Okay, and I want to point out that that polynomial is actually related to the polynomial that shows up in our approximating equation. So this is for non-equilibrium solutions. We have this right-hand side related to the Weierstra equation. So this cubic polynomial over here can be matched with the thing I just wrote down, provided that we link this integration constant e to the free parameter c by this identity like that. And then you see that this holds true just like that. So this polynomial is really the same thing as the right-hand side of our elliptic function differential equation. So turns out that the right assumption for us to make for large y is that the c is picked in such a way that this polynomial, this cubic polynomial, has one simple root, which we call mu equals s, and a double root mu equals p. So if we do that, then that implies a connection between the simple root s and this parameter y, really, this scaling of x, that's the parameter y, that's a cubic equation for s. And if y is a big enough positive number, we can pick the unique negative real root of this cubic that has this asymptotic behavior minus y to the 2/3 plus small as y goes to infinity. That's the one I want to pick. That's the simple root I want to pick. Okay. So at this point, because I know that because I've specified this constant c, so as I have this simple root and double root configuration, now I know what this g function is explicitly, and the effect of it on the jump matrices, I think I mentioned this, is that the phase that is already present just gets modified by basically changing the sign and subtracting g like that. So we're sort of messing around with the phase in our exponents. But then you can draw some sign charts of the real part of this function h, since we know what g is and phi is, we can do that for different values of y. This is a sign chart for y equals 0.4. The blue part is where the real part is negative, and the white part is where it's positive. And what I did is I kind of laid on top of this the jump contour for the problem. That's what this stuff is here. And what I want is that this piece of the jump contour, this is below the simple root, which is this red point, that's all in the blue region. And that means that the exponential that's in that jump matrix is converging to 0 really fast. Similarly, I want the rest of the jump contour to be in the white region like that, and that will have a similar effect on all the exponentials that are in those jump matrices, because the structure of the matrix is different. So the triangular structure is opposite. Okay, anyway, that's what the picture looks like when y is 0.4, but if we start to reduce the value of y, you see what happens is that the landscape kind of undergoes a bifurcation at this double root. This is the double root of that cubic, and then things open up in this way. At this point, I can no longer put the jump contour completely in a part where the color is white, okay, where the real part is positive. So something bad is going to happen here, and that's really what's signaling the edge of this bow tie region. Really, it's the transition from this picture to that one. The bow tie edge is somewhere in here. So the point is that we can put the jump contour on this picture in these two cases anyway, in such a way that all of the jump matrices are decaying very rapidly to the identity matrix, except on this little orange segment, just like that. And on the orange segment, you get a simple approximating, it's a simple jump matrix like this. It's a constant, off diagonal. So you could try to just solve this jump condition exactly. Actually, you could diagonalize this matrix and solve it exactly. So this is what we call the outer parametrics. It's this gadget. So here are the matrices that are diagonalizing this thing. And here is just the piece that's diagonal in the middle. And so it turns out that's pretty good, except there's one point, this point theta equals is, where things are not so well approximated. There you have to create a local approximation that's built out of area function, but that's a standard construction. So at this point, when one compares the parametrics, that is this outer one, most of the complex plane, this inner one built from area functions near is, then you can compare that parametrics to the actual Riemann-Hilbert conditions for M. And what you get is what's called a small norm Riemann-Hilbert problem. That's one that you can solve by iteration, and consequently you can obtain by reliable and rigorous methods. You obtain an accurate approximation for this un of x. It's really built out of this outer parametrics. So that leads to this result here. So there is some critical value of positive value of y, such that this un function evaluated at the argument end of the 3/2 times y is well approximated by the square root of n times u brev, and this u brev is just the positive real solution of this equilibrium cubic equation, just like that. So here's a graph. So that the u brev thing is this red curve, and then for different values of n, we plotted the actual functions, and you see that as n increases, it sort of hugs that curve better and better. So that's the approximation. So this is on the real axis. You can then move off into the complex plane, and you have to deform the picture in the complex plane a little bit. The blue and white regions move around. It's a little bit complicated, but anyway, it turns out that when you do that, you can find that this point, this y critical is like right here. You can actually follow it up and down and get the boundary of this bow tie region. These turn out to be straight lines. That's what happens. These are straight lines that are bounding the bow tie, but these are curves on the outside. Okay, so I think I'll just stop there.
Very much. Other questions?
Sure. So, can this behavior with n be understood from a discrete quantitative equation? Because usually spectral transformations of differential quantitative equations are described by discrete quantitative equations. So,
Right.
can I see this from that point of view?
So I'm certain that it's possible to see this from that point of view. Yes. However, you got to think that it's similar to like it's a similar problem actually to like finding the behavior of the orthogonal polynomials from the knowledge of the recurrence coefficients for large n. So I mean there are problems with that procedure, but you can still learn something in some cases, right? So it's probably analogous to that, I would say. Yeah.
Also, like about this seed solution, so does this cover all the rational solutions? Because is the seed solution unique? Could you
Right.
start from another seed and
So usually what you do is you first establish uniqueness of a certain type of solution by other arguments. So like if you think about rational solutions, it's not so difficult actually. So one thing it's easy to do is to work out the parameter values at which a rational solution may possibly exist. That's the first, right? The way you do that is you just plug in an expansion, a Laurent expansion, and then you look for consistency conditions, right? So that's actually, in all the cases that I'm aware of, that actually gives you the parameter value outright. But still, you have to show that there is a rational solution at those parameter values. But that you can do, that's actually coming through the Schlesinger transformation. So you construct a solution, and then you know that there is one. The last bit is the uniqueness of the solution for the given spectral parameters, and that also comes from a different kind of argument.
Also, a question. I mean, many of us here that I use maybe more to work with Painlev directly and not going to the psi equations.
Right.
And also to study the asymptotics. I mean, it's the Painlev equation of, say, the variable z, and we study the large z behavior. And
Yes.
we also get asymptotic expansions and ideally also the two-parameter trend series. The rational functions, of course, are extremely special, and they're not a general solution.
Correct.
Is there any way of actually using the heavy machinery of trend series to get, say something about rational?
Well, I don't know. I don't know, but it's a different kind of a problem because, I mean, here the thing that's becoming large is like the parameter in the equation in some way, right? As opposed to, I mean, it's also true that the independent variable is large here, because there's some scaling with n. So n is the large parameter in the equation. We're also scaling the complex plane with n. So that's also happening. What can I say? So I guess I think that there should be some way to do that, but because it's not one of the tools that I use, I don't want to comment too much more on it, but I think that there should be some way to do that.
Any more questions? If not, then let's take a speaker again. Because it's Tuesday at 5 o'clock at Muller, we have a line session. We have to cross the field together.